Hello everyone, wishing you all a very good morning. I hope all of you are there in the class and I hope you all can see me and listen to me. Am I audible? Can you just raise hand, Abhiram? Am I audible to you? Okay, I'm audible to Abhiram. Okay, so welcome you all to this new what should I say session sort of thing. It has been quite a while since we had our last class. बहुत पहले हुई थी. It was quite a while, almost around 15 days. So let us have a quick recap in today's class so that we can continue with the classes from the next class. We'll have a quick recap of what we have done in the previous 2 or 3 classes. I think we had already finished with spring force. We had finished with the spring force. We had seen that the spring force is equal to Fs. We write it as Fs. F spring is minus Kx, where x is the displacement or the extension or the compression in the spring. This minus sign indicates that this spring force is opposite to the displacement. That means if the spring is getting compressed, spring force or spring will try to push it out. If the spring is getting elongated, it will try to pull it in. We had done questions on this, and I hope that you remember this. Again, as we did in the last class, now I remember that we had already covered frames of reference. But again, since there was only one class, I would again go and repeat frames of reference. Do you remember frames of reference? Viram, do you remember frames of reference? No. Okay. So I will, I understand that you might not remember it. So I will I do today is go through these frames of references once more so that we are in tune with the class. Frames of reference. What are these frames of reference? Well, we have seen what we have seen. We have seen that whenever we are observing motion or rest or motion are relative terms. Whenever we are observing any rest, observing any body at rest or in motion or seeing any body at rest or motion, we are doing it from some reference frame. If we are the observer, if I am the observer watching a bus or a train, I am the reference frame. Now I can be at rest, I can be moving with constant velocity, or I can be accelerated. Any observer that observes the motion becomes your frame of reference. Most of the questions that we have done up till now, we have taken earth or ground as a reference frame. But in the chapter of relative motion, we have also seen that in some cases, instead of taking earth or ground as the reference frame, it is better to see the motion with respect to another observer, because then it becomes easier to solve the question. Remember the question where there was one car in the ahead and one car backward, then we became the car which is forward, and then we had to find the time when this car, piche wali car, overtakes the next car, ahead wala car. Now in this case, the question becomes very simple if you do it with respect to the other car. You can also do it with respect to ground, but it is always easier to solve the question with respect to the car. These are frames of references. Now, whenever we talk about frames of references, there are two types of frames of references. Two types. One are known as inertial reference frame. The other one known as non-inertial reference frame. Inertial and non-inertial reference frames. Do you remember what are inertial frames and what are non-inertial frames? Abhiram? Do you remember it? Inertial reference frame. What are inertial reference frames? Anyone? Well, for all practical purposes, as I told you, Earth can be taken as an inertial reference frame. So whenever we're talking about an inertial reference frame, the thing that we have in mind is that Earth is an inertial reference frame. Now remember, if we talk in absolute terms, there's no absolute terms, there are only relative terms, but Earth is also not an inertial reference frame. I have told you that Earth is also not an inertial reference frame, but in this case, in the case that we are solving now, in this chapter, Newton's laws of motion, or in whatever you are going to study in the coming 2 years, Earth would be taken as an inertial reference frame, even though Earth is not an inertial reference frame. But all practically it can be taken as an inertial reference frame. Now, if Earth is taken as an inertial reference frame, then we can define the definition of other reference frames which are inertial. Any reference frame that is what? That is at rest or moving with a constant velocity with respect to Earth. Here we have assumed that Earth is an inertial reference frame. So any reference frame that is at rest or moving with a constant velocity with respect to Earth, that it is not accelerated with respect to Earth. It is not accelerated with respect to Earth, is an inertial reference frame, IRF, inertial reference frame. This is how we can define any inertial reference frame. Do we understand this? Any reference frame that is at rest or moving with a constant velocity with respect to Earth, that is, it is not accelerated with respect to Earth, is the inertial reference frame. For example, I am sitting on ground, not moving with respect to ground, with respect to Earth, I am not moving. I am an inertial reference frame. If I am also moving, but I am moving with a constant velocity, then also I am an inertial reference frame. If you are sitting in a bus and the bus is at rest or moving with a constant velocity, train moving with a constant velocity, aeroplane moving with a constant velocity with respect to Earth, all these are inertial reference frames. What are the important things that you must remember about inertial reference frame? Important points. What are the important points that you must remember about these inertial reference frames? Number one, what is number one? Inertial reference frame are at rest or moving with, I hope you are writing also, or moving with constant velocity with respect to Earth. Please remember this. They are at rest or moving with a constant velocity with respect to Earth. Number two, they are not accelerated with respect to Earth. In other words, their acceleration with respect to Earth must be zero. Such reference frames are known as inertial reference frames. Remember one more important aspect. Newton's laws of motion L and M are only valid for inertial reference frame. So whatever Newton laws we have studied till now, Newton's first law, second law, third law, they're only valid. Equations F is equal to ma. All these equations that we have seen, remember, don't forget. They're only valid when the equations or your reference frame is a inertial frame. If you are making your equations from a non-inertial frame, these equations are not valid. We'll have to correct them. Do we get this? These are your inertial reference frame. I think we have done this many times now. I think this is the third time that I'm doing this, if my memory serves me correct. Anyways, since it is after vacations, we must be able to come to speed. Okay, these are inertial reference frame. Then what are the second type of reference frames? The second type of reference frames are non-inertial reference frames. Non-inertial reference frames. In short, I can call them as NIRF, non-inertial reference frame. What are non-inertial reference frames? Now, if you understand what are inertial reference frames, you must be able to understand what are non-inertial frames. What are non-inertial frames? The definition is very simple. Any reference frame that is accelerated with respect to Earth is a non-inertial reference frame, NIRF. Any reference frame that is accelerated with respect to Earth is non-inertial reference frame, or you can say any reference frame which is not inertial is non-inertial. So basically, reference frame, either it will be inertial or it will be non-inertial. If it is not inertial, it has to be non-inertial. If it is not non-inertial, it has to be inertial. So there is no three type. So this 1 and 2 make the entire set. And if it's like binary, you must be knowing what is binary. 0 and 1. Either it is on or it is off. 0, off, 1, on. Only two states are possible for any switch, for any binary. 0 and 1. Similarly, reference frame, there are only two things possible. Inertial, non-inertial. Inertial, non-inertial. So any reference frame that is accelerated with respect to Earth, it is non-inertial reference frame. What are the important points? Let me summarize them as important points. Number one, this reference frame is accelerated with respect to Earth. This inertial frame is accelerated with respect to Earth. Number two, very important point, Newton's laws of motion are not, and this not is very important, Newton's laws of motion are not valid in their original form. Newton's laws are valid, but not in their original form. Something has to be changed. Something has to be added. What needs to be changed or what needs to be added? To make these Newton's laws valid? To make Newton's laws of motion valid, we add imaginary forces. We add imaginary forces known as pseudo force. So, in non-inertial reference frame, Newton's laws are not valid. In order to make them valid, we have to add additional forces which are not real. Those forces are known as pseudo forces. Am I clear? Can I have some reason that we are clear? Those are known as pseudo forces. So the next heading is pseudo force. Next heading is pseudo force. What is this pseudo force? Okay. Before getting into what is this pseudo force, let us try to understand why this is needed. So let me make a diagram of a lift, and I have, so I should make it bigger, and I have a mass hanging from the lift, M. And let us say this lift is moving up with a constant velocity V. Now, I have two people here. I call them Hulks, Green Hulk and the Blue Hulk. My son says that in some video game he has seen alag color ka Hulk, Red Hulk, Green Hulk, Blue Hulk. So Green Hulk and Blue Hulk. Now, remember, whenever I tell you, whenever you are making equations from any other reference frame or from any bus or any car or any train, you always understand that you don't know what is happening outside. So for you, this is the entire world. So this gentleman does not know what is happening in the outside world. I told you, if you are sitting in a train and your entire windows are blanked, you will not be able to make out unless and until you get a jerk. You will not be able to make out whether you are moving or not. If you get a jerk, then you will understand that probably you are moving. If you don't get a jerk, if everything is blanked out, you will not be able to make out what is happening in the outside world. So basically, these two people are going to make our equations. Let us say, what does the Green Hulk make? He writes T. Remember, T is a real force. T and mg, they are real forces. No matter which frame of reference you are writing your equation, the real forces which are there has to be written. Tension and mg, normal reaction, friction we have not come. All these are real forces. You cannot neglect them. Now, this Green Hulk, what equation he will write? You will simply see T is upwards, mg is downward. This block is at rest. That means it is in equilibrium. So we will just write T is equal to mg. That is the equation he will write in this case. And this is an exactly correct equation. No problems with this. This is exactly correct. The blue Hulk, he also sees T. T is real force. He also sees mg. He looks at the lift and he says that, okay, the lift is moving with a constant velocity. That means this block is also moving with a constant velocity. Constant velocity means acceleration 0. There is no acceleration. T is upwards, mg is downwards. T is equal to mg becomes the equation. As you can see, both the equations, whether you look at the yellow one or you look at the green one, both the equations are same. Both the equations are same. No problems. Let us now take the case of this red lift. A similar lift having a block of mass m hung from the ceiling. But the only problem is, the only difference is, this lift is moving up with an acceleration a. Now this green gentleman, green Hulk, is in the lift. This blue Hulk is on the ground. Remember, ground is an inertial reference frame. They both now make equation. Remember, the green one doesn't know what is happening in the outside world. To him, lift is the world. He sees only real forces, T, mg. He does not see the block going anywhere. Block is in equilibrium. He still writes the equation T is equal to mg. From his understanding, this is exactly correct. Nothing is wrong. He does not know what is happening in the outside world. What about the blue Hulk? What does he write? He says, okay, T is upwards. T is upwards. Mg is downwards. Acceleration is upwards. This block is accelerating upwards. The equation that he will write will be T upwards minus mg, which is downwards. T minus mg is equal to ma. This is the equation that he will write because he sees the entire lift going upwards. Which equation is correct? Which is wrong? Well, now you know that the blue equation is correct and the green equation is wrong. And the reason is very simple. Blue equation is written from the inertial frame, but the green equation is written from the non-inertial reference frame, and hence it is not correct. Now, how do I correct it? We correct it using the concept of pseudo force. Now, pseudo force, let us first understand what is pseudo force, and then we will try to correct this equation. What is in non-inertial reference frames to make Newton's laws of motion valid? Newton's laws of motion valid. If you want to apply Newton's laws of motion from non-inertial reference frame, you have to apply this pseudo force. Now for this pseudo force, there must be two things. There must be a direction. There must be a magnitude. What is the direction of pseudo force? It is opposite to the acceleration of the body, not the body, acceleration of the reference frame. The reference frame is accelerating. So whatever is the acceleration, pseudo force must be opposite. If acceleration is upwards, pseudo force is downwards. If acceleration is downwards, pseudo force is upwards. If acceleration is rightwards, pseudo force is leftwards. If acceleration is leftward, pseudo force is rightwards, opposite to A. And the magnitude is mass multiplied by acceleration. Mass of the body multiplied by the acceleration of the body. That is how you apply pseudo force to make the equations valid. Let us go back now. I hope you understand this. Can I have some reason that we understand this? Can I have some reason that we understand this? Okay, great. Okay, let me just, I was just adding a pen. Okay. Now let us go back and see what is happening here. Now this green Hulk realizes that he is in a lift which could be moving. So he asks this blue Hulk, am I accelerating? The blue Hulk says, yes, you are accelerating. He's an inertial reference frame. So then he asks, in which direction is the acceleration? Blue Hulk says, upwards. He says, okay, pseudo force. Okay, something wrong. Pseudo force. Since the acceleration is upwards, pseudo force will be downwards. Opposite to the direction of acceleration, pseudo force is downwards. Then he says, what is the acceleration? Blue Hulk says, acceleration is A. The mass of this body is M. So he applies the pseudo force MA in the downward direction. As soon as he applies pseudo force in the downward direction, it becomes a force. It is not a real force, but for him, it is a real force now. Now, what is the equation he writes? He collects his equation. This is the wrong equation. He sees T upwards. T is the real force, so I am writing it in green. T is upwards. That should be called downwards. Mg is real force. Mg is written in green plus Ma. This is the pseudo force. Magnitude is M into A. And the direction is downwards because the acceleration is upwards. Now if I compare this green equation with this yellow equation, I would see that both the equations are written correctly. Do we understand this now? Can I have some reason that we understand this? How I have written and how I have corrected the equation for the non-inertial frame by applying pseudo force. The direction of pseudo force is opposite to acceleration. The magnitude of pseudo force is mass multiplied by acceleration. Now I'll give you a simple problem. I hope you are able to solve it. Remember, you will have to solve the problem from the non-inertial frame. So let us say, for example, I have this lift which is moving downwards with an acceleration A. I have this mass M hanging in the lift. You have to find out what is the tension in the string. You have to find out what is the tension in the string. You have to solve this question by non-inertial reference frame. Do you understand the question? Can I have some reason that we understand the question? Find out the tension in the string. Okay, I'll give you a minute. So I hope you have solved this problem. How will you solve this problem? You will draw the free body diagram. Mg is downwards, tension T is upwards, as you can all see. But again, you must see that there is acceleration. This frame is accelerating downwards. So I have to apply pseudo force upwards. The value of acceleration is A. So the value of pseudo force becomes mass of the body into acceleration A, ma upwards, ma in the upward direction. Now you see T upwards, ma upwards, mg downwards, T is real force, T plus ma, which is the virtual force, non-real force, is equal to mg. That becomes the equation. From here you can find out the value of tension. Tension is equal to m into g minus a. Do we all understand this? How I have done this? Can I have some reason that we have understood this, sir? Can I have some reason that we have understood this, sir? Okay, great. Now I'll give you one more problem. Again, lift problem. Two problems in the same problem. Again, this is a lift. This is a weighing machine in the lift. And a man is standing on top of this weighing machine. The mass of the man is m. This lift is moving up with an acceleration a. In case number 2, same man, but the lift is moving down with an acceleration a. In both the cases, we have to find what is the reading in the weighing machine. What is the reading in the weighing machine? Remember, we have done weighing machine. The reading in the weighing machine is the value of normal reaction. Do you remember this? Reading in the weighing machine is the normal reaction. So basically, I'm asking you to find the normal reaction in the two cases. I'll give you 2 minutes. So you have done this. Can I raise hand that we have done this? I'll give you 1 more minute. Are we trying? Abhiram, Tanu, are you trying? Please raise your hands if you have done this or you are trying. Okay. Have you done this or are you trying? Okay. Tanu, try. Okay, try. I'll give you 2 more minutes. Don't worry. I'm in no hurry. Try. Okay. Let me help you out. Let us first draw the free body diagram of this man. mg is downwards, weight of the man. The machine is giving it a normal reaction n. So normal reaction n is upwards. Remember, we are inside the lift, green hulk, and we are making the equation from the lift. The lift is accelerated upwards. So I have to apply a pseudo force downwards. So the lift is moving upwards. The value of the pseudo force will be m into a. The man, obviously, I see at rest in equilibrium. N is upwards. N is upwards. Real force. Mg is downwards. Real force plus the pseudo force Ma. That becomes the equation for normal reaction. Normal reaction becomes Mg plus Ma. Do we understand this? Can I have some reason that we understand this, sir? Great. 1 more minute for you to solve the other one, and we'll wind off today's class. Again, we'll become the green hulk sitting inside the lift. Normal reaction from the weighing machine, N upwards, Mg downwards, but acceleration A is also downwards. So you have to apply pseudo force upwards, which is M into A upwards. Now I write the equation N original force, real force upwards, Ma, the pseudo force is also upwards because acceleration is downwards, is equal to Mg. That is your normal reaction. Am I clear? Can I have some raised hands that we understand this? Great. Okay, so I'll wind off today's class with a short recap. We get in tune. So the next class we'll move forward from here. What we have seen in today's class are the frames of reference, 2 frames of reference, inertial or non-inertial. If a frame of reference is at rest or moving with a uniform velocity with respect to Earth, it becomes an inertial frame. Newton laws of motion are only valid for inertial reference frame. Any bus moving with a constant velocity, any train moving with a constant velocity is Inertial reference frame. If it is not inertial, then it has to be non-inertial. It must be accelerated. So any frame which is accelerated with respect to ground is non-inertial. Newton laws of motion are not valid in their original form. To make Newton laws of motion valid, we have to apply unreal forces, imaginary forces, known as pseudo force. Two things you must remember about pseudo force: magnitude and direction. Direction is opposite to acceleration. Magnitude is equal to mass into A. Then we have done problems discussing this pseudo force. In the next class, we'll be doing more problems in this chapter. Until then, take care. If you have any doubts, you can ask me now. The class is over from my end. Take care.